Hey everybody, Milk's here.
And MoNaCo over here too.
Still in solution chemistry.
Yep.
Moving on to lecture number 5 on page 11 and 12.
So you just had a couple pages of practice. Hopefully you tried it on your own before we did it in class. See if you can flex that brain muscle of yours.
Yep, there you go. Now we're going to introduce table G and how I can manipulate solubility.
Right, so we just did table F. Now we're going to G, so it's kind of alphabetical. F, we saw what makes something soluble or insoluble.
Right, what will and won't dissolve.
The rules. And now we're going to say, okay, so if it dissolves,
how can I make more dissolve? How can I make less
dissolve? Basically, it's going to be interpreting a graph, this whole lesson.
This one really will be. And we're not going to get into too much into rates this unit with that. So we're not worried about it. Will it dissolve faster
or slower?
How much?
Right.
Well, let's go quantity on this.
So there's 3 things that can affect the solubility of any compound, like meaning make more dissolve or less dissolve.
Sure. And the first is nature of solvent. So we remember that like dissolves like. So
change the solvent to match the solute. So if you're trying to get something to dissolve, and it won't in whatever solvent you're using, try changing the nature of the solvent.
Right. Go from polar to nonpolar or vice versa.
Backwards and forwards. Right.
Because one of them is going to do it. If one won't, the other should.
Right. And again, we're talking mostly about water here. So in this reference table that we're going to show you, we're always talking about dissolved in water.
Specifically. So this won't have to do with that. Right. This is going to have to do more with the temperature.
Right.
So the solubility of a solid is going to increase as I increase my kinetic energy.
So as I heat up the solvent, those molecules are moving faster and they're further apart. They expand a little bit, which makes more space in between the molecules of solvent for the solute to squeeze in.
Right, but plus now they're moving around with a little bit more force, quickness, and they can pull apart that crystal structure of the solid better.
Yeah, I was taught this word that dissolving is when the solute slips into the interstitial spaces between the solvent molecules.
The reason I don't teach that is because I can't spell that.
Basically what it means is that dissolving involves your solute slipping in between your solvent molecules into what would be considered, quote, nothing, no space. They call it interstitial.
Okay.
At the molecular. But anyway.
Now there is the opposite going on now for gases. If I heat the liquid up, less gas is going to be able to be dissolved.
For the same but opposite reasons. The solvent is moving faster, imparting collisions and kinetic energy to the solute. A gas wants to be a gas, and when it gets hit with more energy,
now it can escape into the vapor phase and he's outie.
Much easier. You know this inherently. Hot soda gets flat fast.
True.
Cold soda keeps its bubbles longer.
Sure, and here's something you might not know. The warm water out in the lake is going to have less fishes.
The hot water has less fishes. Oh, because there's less oxygen dissolved in it.
There you go. And
so fishies like breathe. Somewhat cold water.
So then they can breathe. You get more oxygen, they can breathe under the water.
Fishies like waterfalls. Why would they like waterfalls?
Because it's mixing up the oxygen into the water. Yeah, well, that's why in the tank you need to have that aerator. Yeah,
so
bubble it in.
Stone or
you bubble it in, yeah.
Otherwise your fish is going to suffocate.
Yeah.
So wait, fishes breathe air?
Mister, this isn't biology. We're sticking to chemistry. Yeah. All right, pressure
dissolved air.
Yeah, pressure now only deals with gases and their solubility because liquids are incompressible.
Solids are incompressible.
Solids are incompressible.
You can only compress a gas.
True. So if I push down on that gas,
pressure increases, solubility increases.
Right, and this is why our soda cans are sealed. And you hear that.
They're pressurized.
Right, to hold it in there.
They force extra in there to keep whatever's dissolved in the water dissolved in the water. They don't want the bubbles bubbling out while it's sitting on the shelf.
Right, now I've seen these go away. I don't know why I haven't seen them in years, but they made this. I saw in the soda aisle at the grocery store, they put this screw-on cap that's separate that you buy, and it's got a little pump on the top, like the pump-up sneakers. So you could actually put more air into the top of the soda to push down and keep your 2-liter carbonated longer.
Interesting.
It's a neat little concept.
The reason why this works, again, is because as you put pressure on a gas, it squeezes it into the water. It squeezes it, forces it into the interstitial spaces.
Right, or
between
keeps
the solvent.
Keeps it from escaping.
And at the same time, it keeps it from popping out.
Yeah.
So when you pop the top on your soda, you're releasing the pressure inside the container.
Right.
And it goes out into the atmosphere, and
Sure.
all of a sudden all the bubbles start coming out.
Yep.
Because now they have a vacuum to fill. They can go and fill
Right.
that space that
And
had
if you
been
notice, on a 2 liter, every time you open that thing, doesn't that get quieter and quieter and quieter? And after a day or two,
Right. You also
can
notice,
forget
I
it.
hope, that the 2 liter on the shelf before it's been opened doesn't have any bubbles in it.
No, and if you touch it, it's kind of hard. It's pressurized.
It's pressurized. So you can shake up a can of Coke all you want. There's no bubbles in it until you open the top.
Yes.
So it's like carbonates. It's carbonated water, but it becomes bubbly in the moment that you begin to
Sure.
consume.
This is something we talked about in class.
Great product, right?
Right. If you
it's gonna
drink
be
like a
fresh
half-
bubbles every time you open one up.
If you drink like half of a soda with a screw-on cap,
Mhm.
and you shake it up, you're gonna now
Make it go flat. real
make
quick.
it go flat.
For
real
me,
quick.
Pepsi is way too bubbly, so I have to do that.
Oh,
because
really?
For some reason, the bubbles in Pepsi are extra big to me. I don't
Yeah,
know.
I mean they kind of hurt the back of my throat a little bit, but I think I've associated that with a good thing. Like I want to feel
Yeah,
that
well,
sting a
most
little
people, that's
bit.
why we like soft drinks.
Yeah.
Coca-Cola, on the other hand, is very smooth drinking. It's like a
It
bubble
feels
size.
softer.
Yeah.
It does feel softer.
Soft drinks.
not as crisp.
The soft drinks is because of the bubbles.
Here we go.
Anyways.
All right, 3 different major types of solutions. I'm going to list all 3 first, and we'll talk about what they are. They could be saturated, unsaturated, or the granddaddy, and very rare,
Supersaturated.
supersaturated.
We actually showed a quick video on this.
We did, if you
It was
watched it.
fun, inspired by student curiosity.
Nice. Go with saturated, Mr. Mike.
So this is when the solvent dissolves as much solute as it can at a given temperature and volume. So like if I got a bucket of water at room temperature and it's 1 gallon, I can only put so much sugar into it. I've done this at the restaurant many times myself. They give me the whole packet of sugar, the whole shaker of sugar, and they got my water, my iced tea. Just keep adding it, stirring it, stirring it, until all of a sudden it won't dissolve anymore. It's as sweet, it's as concentrated, it's as saturated as it can be.
Right, like a sponge that can't hold any more water.
Exactly, but this is a liquid that can't hold any more solid.
Correct.
Yeah.
But it's, the analogy works.
Yeah.
So unsaturated then is if I stop adding solvent before I get to that point where I'm saturated. The solvent dissolves less solute than it can at a given temperature and volume.
Right, so you could put more in if
There
you
you go.
wanted.
So I'm not saturated.
Right, it's like you add a pinch of water you're boiling to the pot of pasta.
Yeah, a pinch of
instead of
salt.
like, yeah, I misspoke. Add a pinch of salt to the pasta water instead of like the whole can of salt.
Right. And then supersaturated is a very special case. Not everything does supersaturation.
Nope.
But every once in a while, we can trick that solvent to actually dissolve more than it's supposed to at that given temperature.
Right, and what happens is if it's relatively unstable, sometimes it will crash out and fall to the bottom.
Right, and that's what we like to see.
Yeah.
Generally, we got to heat it,
Right.
and then cool it slow. So if I got, say 60 grams to go into solution, and then I let it
shouldn't have held
cool,
it. Right.
and I let it cool to a temperature where it should only hold 40,
Mhm.
but all 60 is still dissolved.
Right.
Now I'm super saturated, and it just takes a little,
Yeah.
and all of a sudden it's all going to come crashing out.
This isn't a great analogy, but it's like overfilling a tire.
Okay.
Right? Because tires about gas pressure. We're talking about solids dissolved in water here. That's why it's not a great analogy. But you can put more pressure into a tire than it's supposed to hold, and odds are it's not going to burst right away.
No,
But-
but when it gets hot,
It gets hot, you drive hard on it, boom, done.
ruptured tire.
Ruptured tire.
There you go. So not a bad analogy.
Overfilled. Don't get this
Overfilled.
confused with super cool, which might happen to a fresh, pure bottle of water in the car overnight this time of year.
Okay.
I had a bottle of water in there, it was Poland Spring. I'd taken a sip out of it, put the top back on. It cooled down very, very slowly overnight, below freezing. So I picked the bottle up in the morning to take a sip of it, and by the time I put it to my lips, it had already frozen solid.
Wow.
It was super cooled, not super saturated.
Okay.
So it looks similar, but it's not the same. So don't get super saturated and super cooled confused like some of my students did today when they saw the hot ice
okay.
demo. They're like, oh, it's like that bottle of water I had in the car, mister. I'm like, yes, but no.
I was going to say, I wasn't going to get it confused with super cool if you didn't mention it.
You would, but we're chemists. So
Well, hey. Okay, here we go. Now, big bad table G.
it's terrifying.
It is. Well, it's terrifying because look at all that stuff.
There's like, when you're expecting to see one line on a graph, this has got what, 3, 6, 9, 12?
Yeah, so there's a lot going on here. So first of all, we need to be
11.
careful of a few things. So let's try to get through this so we're not here for an hour.
Notice units on the y-axis.
Specifically, 100 grams of water is what we're talking about. So how soluble is some of these solids or gases in specifically 100 grams of water? How much can I get to dissolve?
Because we
at
all
that
know
temperature?
solubility is a measurement of things. Like if I have a swimming pool full of water, I put a buttload of salt in there. But if I only have a cup full, I'm not going to get as much in there. So we had to be specific about how much solvent
Correct.
is involved. And this is 100 grams.
Right, so there's a
Third
big key,
time.
right? Notice there's two different kinds of curves. The solids are going to go up because I can dissolve more solid as temperature goes up.
The
and
gases.
go down because I dissolve less as the temperature goes up.
So there's 3 gases and 7 solids on this picture,
Sure.
this graph.
Yep. Sure. And then next, there are so many different lines and curves on here. Please don't get them mixed up. Identify the line you need and stick to that one.
Right.
Okay? So let's kind of
Actually, how to use and interpret this chart.
how to use and interpret it.
So if you're given a problem and the value falls exactly on the line of interest, we call that saturated.
because these are the saturated lines.
Right.
These lines show me how much will dissolve. And if I can dissolve that exact amount, then of course that's what saturated is. So here's an example. 40 grams, I'm going to talk through this so you guys can hear the microphone good. Okay, 40 grams of NaCl, sodium chloride, at 90 degrees. So the first thing Mr. MoNaCo is going to do when he gets this highlighter up and going is he's going to find NaCl and he is going to highlight that bad boy. Now you need to,
That's this line right here.
Yep.
Relatively flat.
relatively flat, you need to be able to do this mentally. Or, maybe for the first few you can mark it up a little bit. We can always print out more of these. So now let's find 90 degrees.
All right, got it.
90 degrees on the bottom, grab a pen.
Color on
Oh,
blue.
blue.
Okay.
Find my 90 degrees.
90 degrees.
And it says 40 grams. Now 40 grams is on the left, so we're going to go up 90 until we hit the 40.
So I'm looking here.
And notice
To me,
you are right on the line.
about right on the line, so that's how I know I'm saturated.
That is exactly right. So it's saturated because I'm right on the line.
That's all there is to it.
All right, good. Next one. When I have conditions that leave me below the line, then we are going to call that unsaturated. Okay,
what
so
compound are we talking about?
We're going to talk about KNO3
At 60.
at 60. So highlight KNO3.
This big one. Wow, that's a rather steep curve. Means
Nice.
It changes a lot.
It
in
is.
relationship to temperature.
So now with our green marker, let's find 60 degrees.
Okay, I got my 60 degree temperature right there.
And let's go up to 70 grams.
So now I'm kind of just playing Battleship.
It is like Battleship a lot if you've ever played that. And notice where those two meet,
Right here.
right there, is below the line of interest,
This is-
KNO3.
Unsaturated.
So this is called unsaturated.
I could put more in.
I could get more
The
in.
question's going to be how much?
Well, we're going to do that next page.
We will, but here's a hint. It's the difference between those two.
There you go. Good. So as he's getting ready for the next one, if values are above the line, this is what we call supersaturated. So the example we're going to use for this one is NaNO3. So we got to find NaNO3.
There it is. NaNO3.
And notice that the arrow points to a line.
Don't get confused when they cross. They don't change direction quickly, so when they cross, don't think oh, they haven't changed direction. No.
No.
It's the smoothest option.
Yep, the smooth option. So now 20 degrees, 110 grams. So take 20 degrees, follow it up to 110 grams, playing Battleship. Mister, you missed. You did not sink my Battleship. But notice, this particular point is above the saturation line. That's what tells me I am supersaturated.
And the question will become,
How much?
falls to the bottom if
When-
it gets saturated. And guess what? Hint, hint, it's going to be the difference between
Those two spots.
points.
Excellent.
Good.
All right.
Oh,
Oh, there you go. Next page. So we're going to keep at this. You keep drawing, I'll keep narrating just so the volume stays right. Okay, so if I'm going to deal with 90 grams of NaNO3 at 40 degrees, it says saturating a solution, adding solid to the line. So how much more am I going to have to add to make this thing saturated?
So I've got 90 grams in and 40 degrees. So there's my 40 degrees.
Okay.
And there's my 90. So 40, 90 is right here. Right?
Good.
That
Now-
marks the spot, 40, 90.
So what we want to figure out is at saturation at 40, how much would it hold?
how much?
So I'm going to say it would hold about 105 grams.
Oh,
Can you write 105 up there for me?
sure. So this is like, it could, so it's 105 grams
At saturation.
saturated.
And I only put in 90. So I'm going
Minus
to,
90 grams added.
and it's going to give me an answer of 15 more grams I would have to add to get saturated.
So we could add 15 more. And do the math that way, or you can count in 10. So it looks like by 10, about 15. That's about how much you'd have to add to get to the...
Sure. Yeah, I just wanted to show the math to show
No,
that
that's
it really
great.
works.
I didn't realize that. That's fine. Perfect.
Okay, and then let's move on to the next one.
Alrighty.
While you erase.
Color, I gotta go blue again.
Yeah, we're not changing colors this page.
Okay.
All right, but we're going to deal with KNO3.
Okay, I'm going to highlight KNO3's line. I got to find it. KNO3.
And it says how much solute will precipitate if the solution is supersaturated and crashes. So let's find it. 50 degrees.
Okay.
And go
110 grams.
110 grams. Let's see.
Playing some battleship here.
Yep, playing battleship. There we go.
So this is how much we have in there. It's a supersaturated solution.
Right.
And we want to know
How much would it be at saturated?
how much would...
So what's the difference?
Right. So
let's write down our 110 that we got.
So 110 grams added.
And I'm going to say, it looks like the saturation would be at about, would you say 85 or 84 grams maybe?
Let's see. Yeah, we'll do by 5. It's 85. About 85.
About 85.
About minus 85 grams dissolved.
Sure. And so now when we subtract those, I got 15 and 10 is 25 grams of precipitate would fall to the bottom of the flask.
5 grams fall out.
There you go. See, we can play games with this particular chart. Now here comes the most common game that the Big Bad Regions test wants to give us, and they are going to change the amount of water.
Right.
So now just thinking about this, if I double the amount of water, what should I do to the amount it should dissolve?
We're talking about KCl here.
No, there you go. I should just be able to dissolve more.
Well, let's see. Situation is that we got 200 grams of water, 60 degrees KCl.
So let's see how much 100 grams of water at 60 degrees would dissolve. So we follow this up, and I'm going to say it's about 45 grams, right in the middle.
Yeah.
So if I could dissolve 45 grams into 100 grams of water, I should be able to double it if I double the amount of water. So I need to double that amount of solute and say 90 grams, 45 times 2, is going to be able to dissolve. Because notice I doubled the amount of water. Now, I can't promise you what they're going to do on the Regions test, if they're going to double the water or half it. But they're going to do one of them. They're going to do one of them.
Oh, and we will definitely be doing one of those on our part too.
Absolutely. So you need to know that you need to be able to recognize, did I half the amount of solute or solvent, or did I double the amount of solvent? And then I'm going to have to reciprocate that to the amount of solute that it will dissolve.
And in the end of the day, you're reading a graph.
You're really just reading a graph.
Mm-hmm.
This is actually, I think it's a kind of fun graph.
Yeah.
But I can see how it's big and bad and scary when you first start messing with it. We did it.
What else we got here?
We did it. I think that.
I don't know if we click over here. Clicking.
I think my battery died.
Computer error. So there you go. Table G, solubility versus temperature.
Yep. The 3 factors, and how do I use table G?
That's it.
Am I saturated, supersaturated?
We're going to follow this up with a kind of fun little solution demo on the video.
Stay
Us
tuned.
being scientists.